Okay. Hello everyone. Welcome to the week 7 of your problem solving sessions for this course. My name is Raj and I'm a PhD student at IIC. So today we'll do the week 6 quiz, solutions and and week 7 contents, basically classes and objects and stuff like that. And and any doubts you have regarding any of this matter. Okay. Um, let's start. Okay, so uh, week 6 quiz. So let's try to make this a bit interactive. If anyone have any idea on how to solve the first question, you can let me know. Any thoughts? How would you go about, solving the first question? It's about basically just, set operations. So again, that the caret here that is there, this symbol that represents the XOR operation, correct? So any thoughts on how would you go about, solving this question? Okay, so U XOR V, let's say, when you have, does anyone know what the XOR operation does, exclusive OR operation, how you would uh, represent it in terms of the basic and OR operations? So So anything regarding hall ticket and all of that, please ask on the discussion forum. Okay. Um, so U XOR V is basically when you, let's say you have two sets. Okay. This is U, this is V. Okay. So U XOR V is this area, is this content, right? So that's basically whatever is there uniquely common to U and uniquely, uniquely present in U and uniquely present in B. That is basically the XOR operation, U XOR B. Okay. So this can be written as basically your U union. Okay. For union, I will use the plus operation. Here they have used, a single line. Um, or let's just use single sum. Yeah. So U union V, that is basically the whole of the thing. That is this whole region, right? So this complete region will be U union V. Okay. Mm, let me do it this way. Yeah. So U union V, this is the union operation, the green colored one. Okay. And the blue colored one, let's say this is the AND operation. Okay. So it's U and V. And is what? Yeah. U and V. Correct. So basically, we can write the U XOR V, that is U XOR V as U union V minus U and V. Right. Again, minus is the set difference operation. What that tells you is that if I do, let's say, A minus B as a set difference, okay, what that means is whatever elements that are present in B and also in A, those will be removed. Right. So only which are there uniquely in A, only that will be present in A minus B. Okay, this is one way of writing XOR operation. It can also be written as U minus V. So that's basically whatever the elements are unique to U, and then union V minus U. Right? That's basically saying whatever is unique to V. Right? And that's exactly what XOR operation is. Okay. So now what we'll do is we'll look at these different operations and see what will be always true, regardless of what the values in U and V are. Okay, so let's look at the first statement. All the right hand side we will look at. So V, they're asking V union U XOR V, correct? So it's going to be V union U XOR V. We'll again use this idea, that is, yeah, this sort of a system. Okay, um, so it's going to become, in bracket, let's say, in bracket, it's going to give you U or V minus U and V, correct? Okay, so this is now just going to be V or U or V, right? Minus V, mm, yeah, minus V or U and V. Okay, so again, remember, set operation, V or U or V, right? This is basically going to give you uh, just your U or V, correct? So we are saying you take all the elements present in V or U or V, which is exactly just same as saying you take all the elements in U or V, right? So that's U or V minus this operation, that is V or U and V, correct? So this is basically saying that, um, so this, you can think of it like this, right? So it's basically, yeah. So V is there and U and V is this, correct? This is U, this is V, and we're taking this. So this is uh, U and V, you're going to do ORing with V. That is basically taking a union with V. That's going to give you back V itself, correct? This gives you back V itself, right? Now what you're saying, we're saying in the whole of U or V, right? This whole area, this whole union, whatever we have, you remove all the V elements. Okay, remove all the V elements. Then what ends up remaining is basically your U. Okay. Hmm. Hmm. Okay. So hence this is not the, sorry, this is not U. This is going to be U minus V. Okay. So you're saying whatever is there in U union V, right? This area, whatever is present here, you remove all the V elements. So even the common ones are also will get removed, right? That's exactly U minus V. So this is not the right answer. So let's look at the second option. Is basically V XOR U. So this is anyway U XOR V only. So we have no other extra information about how U and V are. I mean, they are disjoint in some sense, right? So that information also, if we use, we have no extra. Yeah, so if we have, so this becomes U or V minus U and V by definition. And U and V is null set, right? Because the given that is disjoint, so it's going to become U or V. So this is also not true, right? Then third option is basically your V XOR with U or V. Okay. So here we're doing the XOR operation. The second argument is basically a OR operation, correct? So for that, what we will do is, again, let's just apply the the definition. So this becomes V, and then ORing with the second set. That's going to be U or V. Okay, second set. Then minus the intersection, correct? V and U or V. Okay. Then what you have now, so V or U or V is again basically just going to be V, and this is V and U or V. Okay. So U or V is this whole set, basically this whole um, set of elements, and then we're saying you AND with V. So you want intersection of the whole set with only with V. That's going to leave you exactly V itself. Okay. We're going to give you U or V minus V. Hmm. So then I'm going to give you U minus V. So it seems to be something wrong here. So U or V is the whole set, and then you intersect with V, you get V back. Okay, I'll check this out later. Fourth option, again, similarly, you can do. So you will get U intersection with, I mean, XOR with V union, V given, or V ORing with U. Okay. So again, yeah, so here you will get U or V or U. Okay. Hmm. And then minus U and, sorry, sorry, yeah, U and V or U. Correct. This is going to give you, so this again, U or V or U. That's great. This is going to be V or U. I mean, correct, U or V, right? Minus. This is again, we're saying the whole set union, and then you and or you take only the common elements with U, which is basically all the U elements, right? So this becomes V minus U. Okay. So I'll check it out exactly what is the right way of getting this. Okay. Fine. Next. So this is straightforward. Again, follows from the definition itself. So when you have U XOR V, we discussed this can be written as U or V minus U and V. Correct? So once you have this, um, so you want this to be equal to U or V completely. So for that, U and V have to be empty. Right? U and V has to be empty. So that's the answer for, that is basically this U and V has to be disjoint. Disjoint with V. Okay. The third question. So we have a min heap. Again, remember min heap is basically where you want the root of the subtree to be smaller or equal to the children. Okay. So in this case, we have the min heap being given. Yeah. So min heap is basically shown as 15, then 27, 33, 39, 66. I have 39 again, 47, 58, and 51. This is 39, 47. That is correct. It's disjoint. So U XOR V is U or V. That's correct. Yeah. So here we're trying to understand what could which of the following could not have been the last element inserted into the heap. Correct. So again, remember in heap in heap we keep the elements in contiguous locations in the array. Correct. So let's say if 58, okay, if 58 was the last element, um, that means previous to this arrangement here, the heap should have been something like this, right? It will be 15, 27, 33, 39, 66, 39, 47. And then this location would have been empty, correct? For 58 to come here, but that's not how we insert elements into the heap, correct? So 58 cannot be the last element that was inserted. Any last element would have been basically any element on this part of the tree, right? So that's possible because let's say if 51 was present, 51 being the last element makes sense anyway, right? Because we are talking about min heap here. If, for example, let's say we had the elements to be the heap to be something like this, 27, 33, 66, 39, 47, and 51, and then 58, right? So then what I can do is I can insert 39, right? And because we're talking about min heap, this gets updated its location to this guy, okay? Which basically will result into your the heap that we had here in the question. Okay, so any of the elements in the last leaf's path from the root, right? That all those are could be the possibly the recentmost element to have been given in the heap. Any other elements is not possible for them to be. Okay. Um, Let me know if this is not clear. I will go through it again if required. Okay. So then we have another min heap, 13, 24, 32, 32, 41, 38, 50, 48, and 40. Okay. Now what they want is, let's say if the last value inserted was 24, then what was the heap structure before this value was inserted, right? Now, again, remember, when you insert in the heap, it basically goes in the last possible location, right? Now, because the heap is in this way, the possible location that the heap that 24 would have been would be here, correct? The last leaf possible, right? So 24 has to come while inserting 24, it would have been here, and then it would have gone through all the above stages. So therefore we have to see a path where 24 can come from whatever location is there currently to this location, right? Basically backtrack its locations, its movement, right? So if I move 32 to here, then I can bring 24 here, and then if 40 was here, then if I had put 24 at this in the new heaps in the previous heaps location, then this heap is possible, right? Let's see it possibly in this form. So if I have 32 here and 32 here, and 40 here, 41 here, 38 here, 50 here, and then 48 here. Correct. So now if I were to insert 24, because we are talking about min heap, this goes in the exchanges to this location, and then exchanges here and here, right? So which gives us the heap that we were discussing, which is given in the first question, in the question, right? So this is the heap that basically is the right one. Okay. So that's basically your first option. Okay. Any further questions on this? Okay. So we'll go to um, yeah. So we'll go to the um, OOPS concepts. That is a object programming concept, right? Which is basically your week 7 lectures. All right. Your classes and objects, and from there we'll see about user-defined lists and so on. Yeah. So um, so what I have here is basically a simple example of OOPS system, right? Um, so let's say we're trying to build an animal shelter system, right? Then what we can do is we can have basically a base class which says that every animal will have some name, some age, right? And some species. But that species, because for the base class, we have no idea, right? It could be any animal. So we'll just name it as generic animal for now, right? And some speak basically, that is what sound they make, right? And info of the animal, right? Which tells about the age, name, and so on. Okay. Now, this is sort of a base class, and we extend this particular class into two possibilities. For example, let's say dog and cat. Correct. So here you can see that in the dog, we are giving the species value very specifically, that the species has to be a dog, right? And whatever name and age is there, that is sent to the superclass. So here superclass constructor gets this all the values from here, and it says, okay, so the object's name and the age will be provided by this particular call, and then we are setting the species here and the breed like this, okay, for a dog. And by repurposing, so basically we are overriding the method called as speak here, right? So here, because we don't know what animal it is, we don't know what sound it's going to make, but dog we know for a fact, and so we redefine this particular sort of a method, which is and we say do this sort of a system. Okay, so it done both. Now, for example, similarly, for a cat, for example, I would have, let's say, different sort of information present. I could have name, age, and let's say not the breed, but the color. Correct. And we set the species to be this cat, and color as a new member, variable in this particular class, right? And we then we also override the speak function, which is basically saying that the cat basically meows. Okay. So this basically tells you, so here name is basically the instance attribute. That is, every instance that you make for animal, for a dog or cat, will have this member value called as the name, age, species, and so on. Dogs will have an extra member value called as breed, and cat will have not breed but color. Okay, so this basically is a way where you can define something generic initially. That's like how we are doing it in the animal class, and then make separate, specialized versions of this particular base class in the derived class. Okay. Then let's say we also create a class for the shelter. So we say the adoption fee is basically the let's say some 100. Okay, so this we are calling it as a class attribute. So this is basically something that is present in this class as such, which will be shared across all possible so all uh, instances of shelter, right? So if I have if I make two shelters, then both of them we will have this adoption fee to be set to be 100. Okay. And then each of this shelter will basically have, let's say, a name for the shelter, and then what are the animals that are present in that shelter. Okay. And funds, for example, is something you don't want the world to know, for that matter, right? So you make it as a private attribute. So private attributes in Python are given as this underscore underscore. Okay. So private is given by underscore underscore, and protected, basically protected attribute is given as let's say some by this single underscore, right? So protected basically means that this can be changed by a only by a derived class of it, right? And private attribute cannot be changed by anything, right? It's present only for that particular object. Okay. Then let's say we define a simple function called as admit animal, and we're just going to say we have some animals in this particular shelter, and list basically just goes through this so-called animals list, and prints you very nicely what the animal info is, right? And for example, let's say adopt function. Here, what you will do is basically you want to, let's say, get the animal from the shelter, right? So somebody's come to take the take some animal. So then you try to we have a function called as the adopt animal. So in this again, remember, so we go through the animals list, and if we find some animal with that particular name, so we remove the animal from the particular list of animals here in the shelter, and we say okay, we now have more funds because we had some adoption happening, so we'll increment the funds in some way, right? um, and this function, basically this get funds function, so that allows you to access the private attribute in some way, right? So this basically tells you, okay, get funds will tell you what the values of the funds are, right? Now, for example, let's say this need not obviously always show the true value. For example, let's say you want to show the funds, but only up to a certain amount, right? So let's say I will keep 50 as my internal, something that I don't want the world to know that I have some reserve, right? So then I would basically show whatever funds I have minus 50. Okay, so this sort of a way you can actually handle basically any sort of private attribute which you're working with, and then how much of it or what version of it you want the world to know. You will try to control that using this get fund sort of a get sort of a methods. Okay, so this basically becomes useful, let's say, when you are dealing with something like a like some value which you know for a fact has to be, let's say, always positive, right? For example, let's say um, def gets to get variance. Okay, so uh, now the idea here is that generally when you're trying to let me just change it somewhere else. Um, right. So let's say I have something like this distribution, some class, right? And def get variance, for example. Now, sometimes it's easy. I mean, it's generally easier to work with the log of the variance in your usual, mechanism, because log of variance. So I can remember variance is a positive quantity, right? Variance is always has to be greater than zero or greater than zero, right? So so therefore, log of variance, for example, log of variance can be any number, right? Any real number, correct? So then what we do is you can then define, um, let's say init variance. Okay. And what we will do is we will say, okay, I will not work with the variance directly. I will work with log of the variance internally. Okay. So I will say self.log variance, okay, is equal to, let's say from math import log, and we'll call it as log of init variance. Okay, and but the thing is, see, the world wants to know the variance value. They don't care about what way you use to compute your internal systems, right? So for that, what we will do is then we'll say, okay, we'll output the variance itself. So I will say x of what do you call that? Yeah, self.log variance. Okay. Now, in this way, you can do that, or you can then obviously define it as a private attribute, and you can say that I don't want people to know what I'm trying to do here. Rather, they'll just be able to visualize, know from whatever get method I provide. Okay, and this will be underscore log variance. Okay, so this sort of things allow your whatever the the people or the code using your class function would classes would basically have some sort of a implementation invariance. So they will just care about the value called as variance, but internally you use log function or you use some other function to work with the variance value, that is your lookout. Okay, so this basically helps you to disentangle implementation from actual usage of the particular functionality. Okay, fine. So then we have things like static method, so which basically doesn't use any of the member attributes here. Okay, so we are basically saying that okay, shelter rules basically has a some rule which is common for all shelters, and this p info is a class method. So basically it's a method for the class that you have defined, that is a shelter class. Okay, so that basically has this idea of okay, what the info is. That's a fee info. That's basically your adoption fee information. Okay, so this will now let's look at the simple example for this. Right. So yeah, so here you can see dog1 is basically a dog object. Okay, with the name this one. So let's just see dog1 dot info. Okay, so Buddy is a dog which is 3 years old. Right? That's the info method. Again, remember info method we have defined in the animal class. Okay, so you can obviously we can obviously change info method also in the respective classes, derived classes, but we haven't changed it, so it falls back to using the info class from the animal this one. Okay, so let's just see in control wise how does it come here. Okay, so yeah, so as you can see, when I call dog1.info, because because the only method that provides the info, the only class which has the info function definition is the animal class. So it goes back to animal class and prints from the animal class. Okay, so if I were to, let's say, redefine it here, right? So let's say if I do info and say Buddy dog is and itself dot speak function. So I'm calling the speak function here again. Something like this. Okay, so this will basically go end up calling the I should put here. Let's just put the breakpoint here. Yeah. So now in this case is going to go to the dog wala info implementation. Okay, not the animal implementation, right? But let's say sometimes what happens is you want whatever has is being done in the superclass also, and also add something more on top of it, right? So what you can do then is you can just call the superclass like this. The method for that, right? So you can say dog comma self dot and then say info. Okay, so let's say this is super class info, right? Is this, and then I would say okay, I want to do something more on top of this, right? So the super class info plus, and then have the other extra information here. Self dot e. Fine. So let's just see how the control flows here. So yeah, so as you can see here, first it's going to come to the animal class. Let me put here also. Mhm. So the function that is called is basically the dog info function. Okay, that has internally called it's calling the superclass function of info. So then it goes here and it says, okay, give me whatever is the string present here. So that comes up here. So we have the superclass info being this simple string, buddy dog 3 years old, and then we are appending something more on top of it, and then we get on the screen. Um, we're not printing it. Okay, so let's just print that. Yeah, so we see that. So then we see on the console that we have buddy 3 years old. So this part came from the superclass, and then we are saying, okay, we add something new on top of whatever the superclass returns. Fine. Um, then let's continue and I'll see. Okay, so we have a city shelter called the shelter of happy paws. Okay, so this is an object called shelter, right? And then we're saying, okay, we'll admit an animal, the two one dog and a cat. So yeah, huh. So this is the information we have from the admit animal function, and then we look at the whatever the animals are present in the shelter. So for that, when we go back here, yeah. So we have two. Okay, and then we're saying, okay, once we adopt, let's say buddy. Okay, so what will happen? So we have an output saying that okay, buddy was adopted. Shelter funds are updated. So here again, we are using the get funds function. So ideally, society shelter dot where is that? Yeah, yeah. So underscore funds. This you cannot basically use because of the fact that it's a private attribute. So the only way to for you to get the the funds is basically being able to do this city shelter dot get funds, right? And we'll see how it comes here. So now we are inside the class. So once you because the control is here, we can try out what the self dot funds actually is, right? So that's uh, Hmm. So that also doesn't allow you to get us this one. So that then we see here it's 50, and then we have the shelter rules present here. Okay. Um, again, remember. So this sort of an idea that we have that we discussed here, right? So basically, the info function calling the superclass info function. That's exactly what's happening here also, right? So in the constructor of this dog class, we're calling the superclass constructor. So this basically sets up some of the variables that we have. There is a name and age and so on and so forth. And then we are adding some extra additional information, that is species and breed, right? So again, remember we were giving species some generic animal as a string for the species. That's exactly what will be set until you execute this particular line of code, right? So let's just look at that once. Yeah, so we are at this line of code that is your creating the dog variable, right? And when you're so now what has happened is we're done with the superclass calling, right? So if I do self dot species, right? So this is the value which is set by the superclass. We now want to override that. So we have done that using the by calling an explicit sort of a variable value here. Okay. So now if I do self dot species, it becomes dog. Right. So this is how your oops functions, I mean, oops concepts here are present. There are other concepts like abstract classes and all of that. We're not getting into that right now. We can probably do it the next week if it's required in the this one. Okay. Any thoughts or doubts? Let me know. Okay. Um, yeah. So with that definition of how to define a particular, class and all of that, and what member values are, what member methods are, so then we can do the idea of user defined lists, right? So where you're defining, a linked list idea, right? So basically where you have one node pointing to the memory location of the other node, and you use that to basically traverse the list, or maintain information in the in the in a sequential manner, right? So this is your given code in the system, right? So let's just see if what we can do. Um, so let's say n is equal to node, right? So if I do that, again, remember here, because we haven't provided any value to n, right? So n dot empty, yeah, and under empty is going to be true, right? So it's an empty list in some sense, empty linked list, right? So then if I were to create the node with some value, let's say 20, right? This tells you that, I mean, this tells us that n or empty is false, that there is something present in it, right? And we can look at the um, elements in this. So here node, so next is none and value is 20. So next is none tells you that there's only one element in this, right? Then let's say we try to append a value, right? Let's see if we can append something, append, and we are trying to append some, let's say 30 here. Okay. So if I do that, now you can see what n corresponds to. So n has a value of 20, and the next value, the value called next, that is again pointing to a node itself, and that has a value of 30, right? So in this way, we are able to store values sequentially. That's the idea in this linked list, right? Um, so that's append idea. If you want to, let's say, insert, again, remember in insert, there was a issue, right? So if you have to insert, because the way we are pointing, I mean, the way we are storing the data, let's say it's something like this, right? So this is none, this 20 and 30, right? If you want to insert, we cannot change the way it's pointing to the initial value, right? If let's say n is pointing to 20, it needs to point to that 20 itself. But rather, what we can do is whatever value we get, right? New value to be put, let's say 40 here, right? So what we can do is you can just change the values present here, right? So we can make this point to this guy, correct? And then make this to be 40 and this to be 20, right? And make the connections in this way. This has to be pointing to this guy, right? So then what will happen is you will have I mean, you'll have a representation where n becomes n has the first element has 40 in it, right? And is pointing to a node which has 20 in it, right? And this guy is going to point to 30. Oh, sorry, yeah, this is not required. Yeah. So pointing to 30, correct? So in a way, we have inserted 40 in the first location, right? That's the our final idea. So hence we do that here. Okay. So let's just go through it. Yeah. So let's say we want to insert 40. Yeah, so first of all, if it's empty, then it's straightforward. There's nothing to be done. So that's trivial case. We'll move forward. And we're now creating a new node, right? That's going to be your new node that's 40, having 40 in it. Now remember, self is basically the value which has 20 in it, and new node value is 40. Okay, so what you're doing is we're exchanging the values between the new node and the self pointer, which has 20 in it, right? So self dot value gets the new node value, and new node value gets the self dot value. So this basically gives you this sort of an idea, right? So the self is now pointing to a value called 40, right? And new node has the value 20. But again, remember, we want to be able to point to the currently we have just changed the values between the nodes. We also need to do the plumbing of the next pointers. So that is now then here done here. So where you say that whatever the new node was made, you point to that node now, and whatever I was pointing to previously, that has to be pointed to by the new node. Okay, so that is now done here. Okay, so here you can see this will basically end up becoming a so now 40, then the next node becomes 20, and 20 then points to 30, right? Which is exactly what we wanted in terms of the list order, right? It's 40, 20, and 30. Okay, fine. This is how insert works, and then deletion has other issues in them, especially when it's the first node. Correct. So here we are doing, let's say, delete by value. Okay, so let's just look at that. And dot delete, let's say if I do 10, um, let's just leave this. Yeah. So first of all, it's not empty. So let's just do that. And first thing is now I want to delete a node which has the value 10, right? There's no node like that. So let's just see if it's able to find out properly. So first of all, it'll check for every, this one that is there a like is the value correctly pointed to this or not, right? So here it's not true. So and then we keep on going to the next value, right? So in case so where the current value is present, right? So that's we are going to do that. And again, remember, it's a recursive call. So we are going to, so here self dot next is a node, right? And its delete function will now be called. Okay, so when let's say if that is the initial node in the list, that its delete function is called. Okay, so if I continue here, I come back here. So now here the self has become 20, right? So it was 40, 20, 30 in the order. We are now saying you don't consider 40, you consider 20 as the initial sort of a list element. From here, you try to delete the value 10, right? Um, and then we do that here and then come back here and then say, okay, try to delete this, the next element again, 30, right? And 30 also doesn't match, right? Self.next.delete is only called if the next is none, not none, correct? So here in this case, so if for 30 it was none, so hence we came back out of it and we are back to the 20 wala location. Okay, so here we see again self.next.value is not none. Um, and then we are again back to the 40th location, 40 wala list, and back to this and saying that okay, there was nothing to delete, so there was no operation that happened here. Okay, so if I were to now, let's say, try to delete the value 20, right, which is in the center of the list now, right? So let's just see how that works. Yeah, so first we'll see that whether it is value is matching. No, so then move on to the next one. And here now we say go to the next one, and here we say okay, we found the value, right? So once we find the value, what we are going to do is we're saying going to say you make the current value to be none, okay? And if the self dot next is not none, that is there is something pointing to the next element, right? So here you can see the value is set to none, but the next is still pointing to the 30, right? So what we're going to do is we are going to make the plumbing now. So we're going to say, okay, if it's not none, you set the value of the current node to be whatever is there in the next node. Okay, so here self dot value becomes next dot value, which is 30, right? So I can see here value was it was 20, it was made none, and then we said make it to the next value, which is 30, right? And then whatever is the next pointer of that next node, make it the current node's next pointer. Okay, so that becomes basically none here, right? Because there was I think after 30, so that becomes your next pointer, right? So that basically was done at 20, and then we finally come here and we say, okay, if the next value is not none, if it is none, and then you set the value to be final empty list, right? That's your deletion process. So here we have seen that 20 got deleted, correct? Now this becomes complicated a bit if you want to do 40 deletion, the first element deletion, correct? So again, so first we check whether it is value is true. Yes. So self dot value is first we set it to none. Again, remember we have value is 40. So that this becomes none first. Then if self dot text is not equal to none, that's true because it's pointing to 20. We set the value to 20 current nodes, and the next value is pointing to this current value. So now it becomes 30, right? This is exactly what we have. Right? So we're just basically plumbing. We are saying you copy whatever is there in the next node to the current node, and then you just make that next node whatever is there free of memory. Okay. Any doubts in this? Any doubts? Is everything clear? So str of n you can do to look at how the so this is just basic idea where you just try to iterate through the values in the node, right? And then see what values are currently present and so on. Or print it, right? So we added 40, we had 20, we appended 30, inserted 40 at the beginning, and then we deleted 40, right? If I don't do that, you just see the 40, 20, and 30. Okay. Any any doubts? Any thoughts? Um, so if you had to, let's say, for example, so this is basically something called as a singly linked list, right? So there are other ideas called as doubly linked list. Any thoughts on, so see, here the point is, let's say if you want to go from 20 to back to 40, right? So while iteration, it's not possible to do. I mean, you'll have to maintain two kinds of pointers and all of that. In doubly linked list, the idea is that you can go front or back to the from one node, right? Either go forward or backward. So if you have to implement something like this, how would you do it? First of all, what will be the way you will define your node to be? Any thoughts? In doubly linked list. So see, we are able to traverse through the list because we're keeping track of the next node and so on and so forth. So here we'll have to keep track of two things. That is what is coming next and what is coming, what was there previously, right? So your node class, right, will basically need to have three things. One is your value, right? Obviously, whatever was present, the next, and also the previous. Okay, so you can define something like this. Let's say value here, and previous will point to whatever the node was there here. Okay, and the next of the previous node, obviously, uh, let's just 1 second. Yeah, so the previous will point to this node like this, right? And this guy's next will point to this guy, and then similarly here, this will point to this guy, and this will point to this guy. Okay, so if you are in particular, let's say if you're in this particular node, right? If you want to go forward, you will use the next pointer. Otherwise, if you want to go backward, you will use the previous pointer, right? So here again, remember, so during insertion, deletion, all of that, you need to be careful and update both the next pointer as well as the previous pointer. Fine. Okay. Any doubts till now? Fine. So yeah, now we'll go through something called as the tree. So binary search tree idea. So does anyone want to tell me binary search tree and heap, what are the main differences? Both are trees, but in what way do they differ? At least in terms of implementation, if you think about it, how do they mainly differ, binary search tree and heap? So one thing is that basically in your heap structure, left is less than root, less than right. Yes, this is in case of which. So left is less than root, less than right in what? In which one? In binary search tree or heap? In BST, right? So in binary search tree, your left child will be less than the root child. I mean the root, and which will be less than the right child. Correct? In heap, the idea is that your root will be greater than both left. I mean, if it's a max heap, left and right. So there is no ordering between the left and right, by the way, right? So here this inherently gives you an order that left has to be less than right. Correct? This is a main sort of an idea. Both are trees, but the way we are using it is different, right? And again, in heap, if you remember, we store it as contiguous, values in an array. But binary search tree need not be like that, right? It can grow very long. So in heap, um, if you have to store any values, you would store them as nice little lists, correct? One after the other. And the first one is the root, and the second one is its left child, right child, and so on and so forth, very nicely present. In binary search tree, that sort of a thing is not possible. So here, hence we define a special sort of a node, or tree basically in the code, right? Which has a value assigned to it, and also has the pointer to the left child and the right child. Okay, so hence we need this specialized sort of a mechanism to develop this binary search tree. Okay. Um, then in binary search tree, yeah. So your binary search tree allows you to do the binary search in a very straightforward way, right? Sort of, it's actually sort of like a tree version of the binary search algorithm, right? Your heap allows you to do your sorting, right? So heap sort basically depends on the idea of heaps, right? So where you store values in a min heap or a max heap sort of a scenario, and keep deleting the max element as the root, right, from the heap. Okay, fine. So with this, let's go to this tree implementation that was present. They have a print option on it. Yeah. So yeah, so we'll start with the first element, let's say, right? So tree, or t equal to tree, right? Um, so again, it's an empty tree, so there's nothing to visualize in the tree for you, right? If I do 20 and then t dot insert, right? Value like 30. Okay, so this will see the point is, whatever the first element is present, that becomes the root, right? So that ends up dividing your tree into two halves. Whatever the elements are there, smaller than 20 will go towards the right, towards the left, and which are greater will go towards the right of the root. right? So now the thing is, if let's say your first element was a very small number, right? And you end up getting a lot of larger numbers than that small number. So your tree will become sort of like a very weird looking sort of a tree where you have a lot of elements on the right side, but very small elements, very few elements on the left side of the tree, and vice versa, right? And this can become problematic in case you are trying to, optimize your, searching technique and all of that, right? So hence we have to go to balanced trees. We're not going to get there, but that's the idea. Okay, fine. So with this, let's see. Um, how it is. It's 20 and 30. So this is the in-order traversal. We'll do that in a bit. But for the before that, let's just look at what values are present. Okay. Yeah, so tree is first of all 20. Left is nothing, right is nothing, and then we have 20 here. And then once I insert 30, as you can see, 30 is on the right side of 20, right? Which makes sense because 30 is greater than 20. Okay. Um, right. Now, oh, yeah. Yeah. Okay. So the way to insert is quite straightforward. You just basically see where the value should have been there. If it is not present there, we just insert it there. Right? It's very straightforward in that way. Okay. So um, let's say we insert a bunch of elements, 10, 40, right? 4, and so on. Let's just see the tree for all of that. Yeah. So here you can see the value at the root is 20. The right subtree has 30 and 40. So first 30 and then 30 ka right is again 40. Left has first 10 and then 10 ka left is again 4. 4. Okay. This is how your tree was made. Um, Now let's see about the deletion process. Correct? Deletion is where things become a bit hairy. Um, yeah. So for that, what we'll do is we'll define a few things. Hmm. Let's make a tree like this. It's 30, 35, 30, 8, 22. Yeah. So 25, 40, 22, and 28. Okay. So I have 20, 30, and let's have another 10. So yeah. Yeah. Correct. So here, so have this sort of a tree where, yeah, here we go. Yeah, so 20, 10, 30, 25 when I insert, it's going to be, it's greater than 20, but smaller than 30, right? So it'll be on the left side. Then 40 is going to be more than both of them. So 40 is going to come here. And 22 and 28, both are greater than 20. So they'll be in the right subtree, both smaller than 30. So left subtree of 30. And one is more than 25, that's 28, right? And then 22 on the other side, correct? Okay, so now let's see if I have to delete, let's say the value 10. Okay, so e dot delete of 10. Yeah, so empty is fine. That's all okay. So now what we're saying is if v is less than self dot value. So basically, first we need to find the value to be able to delete it, right? So this is basically your finding procedure, right? So where you say keep trying to do the your binary search idea here basically, right? And here then we say okay, we'll try to delete in the next, I mean the left subtree, right? So we come back here. Now remember, now here we're in the left subtree. Remember, this is it's a recursive call. So self dot left dot delete of v we call, which is hence we are on the subtree which has 10 in it. Correct. So now here we see, okay, it's not empty, obviously, and we come to the condition where it's actually equal. Correct. So if it is equal, that's exactly where these conditions will come in. Now we say, is it a leaf node? Which is in this case, yes, it's a leaf node. So if it's a leaf node, you can just make it basically saying that, okay, this thing doesn't exist anymore, right? Sort of. So for that, what we'll do is we look at the make empty function. Yeah. So make empty function, we say, make the current node to be, having no value in it, left, right, all of that becomes empty. Correct. So that gives me here, correct? This becomes your empty tree. And um, yeah, okay. So now if you look at the tree, you'll have your left subtree had basically none in it, 10 before, and now it has the none value, right? Basically having nothing in it, right? That's your empty set in some sense. And here you can see the right subtree is basically untouched. Okay, 30, 40, and so on and so forth. Right. So this is very straightforward condition. So where we looked at a leaf node deletion. Okay. So now let's try to delete something a bit more complicated. Mm, left is empty. So let's do that. Huh. Let's remove 22. So if I remove 22 from here already, I don't insert it at all, right? And if I try to remove 25 now, okay, so we'll now come to the case where your left subtree was empty and there's something present in the right. Okay, so and then let's remove 25. Okay, so let's just see how it goes. First of all, yeah, so we first need to traverse the whole segment. So here 25 is greater than 20, so we go to the right subtree. Um, right subtree. So now we are on 20, we are on self is 25. Hmm. Self is 30. Yes, correct. Yeah, self is 30. So self value. So now we'll go back to the left subtree of 30. That becomes your 25 now. So the current value is 25, which is what will match. So let's move to the matching condition. Yeah. So first thing, it's not a leaf, right? Because it has a element 28 below it. Correct? So it's not a leaf, a node, but the left is empty. Correct? So self dot left is empty. So what we do is we basically just copy whatever is there in the right node. Right. So again, remember, so here, if you want to remove 25, 28 is a natural, child of 30, right? Because now what will happen is, because 28 is less than 30, while being greater than 20, the root node, right? So only one value needs to be updated here, right? So that we'll see how it's happening. We just basically copy whatever is there present on the um, right child, right? So let's see here. So yeah, so self dot, huh, self dot empty, self dot left is empty, self dot right is what we need to copy. Okay, so we'll go here, um, and basically copy the right child. So self dot right dot value, that's correct. Okay, that gets copied to the self dot value itself. That's 28 here. Self dot right dot left, that is none, that gets updated to the same none here in this case, right? And then comes here, right? So all these are basically none, and this ends up cleaning up the tree in this way, right? So here we were in the subtree where we had 25, right? We had found 25. Now that all the values that are present in 25, that particular node object now has 28 in it, right? And is a leaf node because the left and the right both are basically empty, right? So that that cleans up here. So here we were here on the left subtree of 30. That gets cleared up, and then we are back in the right subtree of 20. That gets cleared up, and we are back here. Okay, so here again you can see the tree. 20 is a root, 10 is a left subtree. Right subtree you have first 30, and then 30 may say 28 and 40. Okay, so these are we have updated, deleted 25 if 22 was not there. Let me just delete that here. Yeah, so we try to delete this. Okay, now let's look at the similar example, but with some additional complexity. 25, 28, and 22, right? So where the idea is that now you have something present on the left subtree also, correct? So yeah, 25 is we'll type delete. Uh, yeah, so let's just go that here. And we are now first obviously trying to search the element. We are in the right subtree first, then the left subtree will start. That is part of left of 30, correct? Right? And now we are in the condition where it matches, right? This is the subtree with 25 as a root. So first of all, it's not leaf, right? It's not empty. So now we want to find the maximum value in the left subtree. And that's your self dot left dot max val. So max val, let's just see how it goes. So yeah, so maximum value in a tree, basically you will keep on getting by following the right side of the elements, right? So the right subtree will basically have the elements which are greater than the root and so on and so forth, right? So here we are trying to do that itself, and we are saying that okay, if the right is empty, then you can just take the current one. Otherwise, you need to go back and you need to find the maximum value of the right subtree of the current node, right? So again, we'll come to that in some time. But here again, remember, so now your left dot max val, right? That was basically 22, right? In the left subtree, the maximum value was 22, right? That's the idea. So now 22 is what we want to set it up here. Okay. So and we'll say you delete the value of from the left subtree of the whatever value we got, right? So 22 has been put here, and now you just delete this 22 node in this subtree, right? So that's exactly saying like it's like calling the delete function on a new whole subtree with this particular given root node. Okay. Now in this case, because that leaf node is a um, yeah. I don't know why we didn't reuse that. Yeah. So because that leaf node, because that node is a leaf node here. So as you can see here, the self, quantity is basically the node 22 with having no child left or right child. So that ends up becoming the um, leaf node, and then we just make that particular node as empty. That's it, right? So that cleans up this particular value function. Right, so 22 has become the new location at 25. Okay, so this we continue here, and everything ends up returning. So this is what we have the final tree to be, right? So where 20 is a root, 10 is the left child, right child we have 30, and its left child is 22 now, the new value. Okay, so this is exactly what we did. So we said we want to remove 20, so 25, right? So we found the maximum value in this whatever subtree remains, right? And get that value put here. That's it, right? Okay, so this is about deletion and insertion in the uh, in a binary search tree. So with this property, what will end up happening is you will have the elements present. So if 22 comes here, all the elements which are present in this whatever remains the subtree to be will be smaller than 22, right? Because we're choosing the maximum value, which is the whole point of this binary search tree. Your root has to be between your left and the right subtree. Okay, fine. Now we can also do something like uh, t dot. Let's look at the Maxwell function in a bit more detail. Um, yeah, okay, insert is fine. Find is okay. Hmm. So in the Maxwell function, um, huh. So in the Maxwell function, so we're saying that whatever is the uh, oh, is in a delete method still. Okay, so save that. Hmm. So the tree we have is basically having 20 and all of this. So we want to find the maximum value. Maximum value is will be present mainly will be present in the right subtrees only, right? So the right is empty. That's fine. That's basically whatever is there in the currently. And we say if we do a recursive call here, we say you find the maximum value in the right subtree. So this goes on going forward. So here we have the 20 as the 20 as the root. So we'll try to find the maximum value in this subtree, which is where the root is 30, right? So as you can see here, we are in the 30th subtree. Again, we continue and we say you find the maximum value in the right subtree. Right subtree is having 40 in it. 40 is the root, right? So now we say, okay, we have found, I mean, there's no more right elements left. So whatever is there currently, that's the maximum value, right? That becomes 40. Okay, that's the Maxwell function. That's the Maxwell function. So you get 40 as the right output. Okay. So then, yeah. So now let's look at the in-order traversal. So in-order traversal is basically you want to uh, print or basically, traverse the list in such a way that you process the tree in order of whatever is the values which are present, right? Now, given this very simple local rule that the left has to be bigger than the smaller than the root, which has to be smaller than the right. This imposes a global order, which is exactly what we use to find out the do the binary search program. So in this case, what we're saying is we say so here in order a function as such returns a list, correct? So this ends up giving a list. Then we're concatenating that list with the current value, whatever was there in the self condition, and then we get one more list from the right side ka subtree ka in order, and you concatenate all these lists to get the final in order traversal. Okay, so let's look at that. E dot in order. That's anyway happening in the string function. So that, yeah. Huh. So in the main function first, right? So we have it's not empty, obviously. So here we have first what gets done is basically this left dot in order, correct? And just to make things a bit simpler, let's do this. Left in order is this value, right? Then I have right in order is this value. Again, this is how I'm just giving these different names, but ideally you would want them to be processed in this particular order itself. Okay. Um, yeah. So let's just do that. Huh. So main root, right? First, left in order. So the left is basically 10, a subtree with value 10, right? Now we are again in that subtree itself. That is basically 10. Here we have a check that whether it is empty or not, right? So it's not empty. So then we again continue its left node, which is basically empty. So that returns an empty string. Okay. So remember, here we are in the left subtree, the only the 10 one, and here the left in order value is a empty list. Same thing happens with the right in order, right? So in this 10 subtree, when we're trying to evaluate, we got the left in order to be empty and right also to be empty lists. We are now concatenating three lists here, which is basically this left in order, self dot value, and right in order, right? So that gives you a list with a single element, which is 10. Okay. Um, yeah. So then we can, so this was your left in order of for your the main root, the value with 20, right? We now continue with the right side subtree. So for that, we then continue here. We say, give me the different values. Yeah. So here, this is the left in order for your 22, correct? And root that again comes back here. uh, we have gotten the right in order, the correct left in order for your 25 root. That's your root element here, correct? And this similarly will keep on going. And yeah, let's run through a couple of things. So now you can see here for the right element, there's a 30, right? The in order is going to be 22, 25, 28, and 40. So 22, 25, 28, right? Then there's a left in order, and the right in order is 40. So the complete in order will have the values in sorted list, right? Which is like this, correct? And this becomes the right in order for your the main root element. And now we finally get the output to be the complete elements in the proper order that we have inserted. I mean that exists. Okay, this is your in order sort of a computation. So there's another idea in this, which is also part of your, I think, quiz in week 7, pre-order and post-order. Okay, so I mean, post-order is present in your, in the quiz. Um, uh, okay, so before that, this in-order traversal, we were going and doing this, check with is empty. Can we do is leaf? Can I do a simpler condition like elif self dot is leaf function? If it is so, then what do I return here, by the way? What is the in order for um, what is the in order for leaf node? What should I return here? Any thoughts? Anyone? So remember, we want output to be a list element, right? A list data type, correct? So if you have only one element in the whole tree, right? It's a leaf, right? It's also a root. It's also a leaf. So if it is a leaf, then there's nothing to be, I mean, there's no left subtree, no right subtree, nothing like that. So basically the in order traversal will just be its own value, right? So you can just write, and because we need self dot value, you're correct. Somebody who said, yeah. So self dot value, that's correct. But again, remember, it has to be a list, right? So we'll have to return self.value like this. Okay. So it can make, I mean, some of the work that was happening here a bit simpler, but that's the idea. Okay, fine. Now, in post order, so the idea in post order, let's go to your week 7 quiz. Um, yeah. So in post order, the idea is that you traverse the vertex of a binary tree as follows. You first print the left subtree in post order, then you print the right subtree in post order, and then you print the root, right? So if you have to do something like this sort of a functionality with this function called as defined post order, how would you write the code here? What will be your out? What code can be written here? Again, it's very similar to in order traversal function that we have. Um, anyone want to take a? Anyone wants to give a try? Let me put it side by side here. Okay, so you print the left subtree in post order, then the right subtree in post order, and then you print the root. Print in the sense basically process it in some way, right? That's the idea. Anyone? So first condition, obviously, just remember if it is empty, right? Obviously, there's nothing to be present here. So that's we're going to copy exactly what happened in the in order, right? There's no value present, so there's nothing to print, right? Similarly, again, let's do self.isLeaf function. Same idea again, right? Because there's only one element in the list, right? In the tree, hence it becomes a leaf, right? So if there's only one element left, so then there's no left subtree, right subtree. It's only the root, right? Hmm. This is where the main magic happens. So uh, your left post order will basically just be the left dot self dot left dot post order. Okay, right post order similarly, same thing. Because see, what we want to do, so these two lines that we wrote, that basically captures the idea in the first two bullet points, right? So print the left subtree in post order. So left subtree also you have to process in a post order itself. So that's exactly what we're trying to do here, right? So left dot self dot left dot post order. Same thing with the right, this one. Now for the current value that you have, that is once you get the post orders for both left and right subtrees, then you print the root, right? So then you say, okay, return. In this case, it will be left post order plus right post order and then plus your self dot value. Okay, does that make sense? Right. So here we had left in order first, then the value, then the right in order. Here we have the left post order, then the right post order, and then the value. Okay, so this is called as a post order traversal of a binary tree, generally speaking. Okay, so let's just see the way it, what comes out of this sort of a, you know, post order. Okay, so let's try to get this for the current tree that we have. Okay, so it's 20, 10, 30, 25, 40, 22, 28. Okay, so first thing is that you try to first evaluate the left subtree in the post order format. So it's a leaf node. So we're just going to print 10. Simple, correct? This is the first element, right? Then the right subtree. So this left subtree is over for 20. Okay, right subtree. So now for this particular subtree, again we have to apply the post order rules, which is basically you do the left subtree, then the right subtree, and then the root. Okay, so then again we are now in this subtree. left subtree of 30. Correct? Again, it's a subtree. So again, we go back and do the left subtree first. So this is the left subtree you get first, right? Then, so therefore, now there's nothing left after 22. So we then print 22. Okay. And then, so for this red subtree that we have, left is done, right is next, that is 28, and then the root, that is 25. Okay. So this finishes the red wala part. Okay. Then what we have, so this finishes the left subtree of 30 ka root tree, right? Now the right is pending, right is 40. So I'll put 40, right? And then the root of this 30 subtree. So then you get 30 here, right? So this finishes the post order traversal of the right subtree of 20. Final root is 20. Okay, this is what we get. So 10, 22, 28, 25, 40, 30, and 20. All right. Does that make sense? So in the similar way, we have something called as a pre-order traversal. So pre-order traversal is basically opposite, right? So you say you print the root first, then the left subtree in the pre-order, and then the right subtree in the pre-order. So always left will follow right. The root position changes in these three orderings. Okay. So if you have to do that here, any thoughts how we can write this code? Anyone want to take a guess on what? So what will be our first statement here? You can unmute and say. So first thing, obviously, we'll look at whether the tree is empty or not, right? Simple conditions. Self dot is leaf. Again, remember for leaf nodes is just going to be the same value in a list format. Correct? Same thing here because there's no left subtree, there's no right subtree, and so on. And then comes the magic, which is basically, let's say, left pre-order is going to be the left subtree, and we want its pre-order function, its pre-order traversal. So we'll do that. Then right pre-order is going to be self dot right dot pre-order. Correct? Then now here's where the final thing happens, which is basically saying you first have to process the root first, right? So that becomes your self dot value, and then your left subtree, that's left pre-order, and then your right subtree. Okay, so very simple sort of an idea. Okay. So you get the root first, and then the left subtree, and then the right subtree. Again, in the left subtree, your root first. That's over here in this case. Then the root first, and then your left subtree, right subtree, and so on. Okay. So you can try out the pre-order traversal for this. It will basically end up matching what we have obtained here. Okay. So any doubts, any questions on the content that we have? Yeah. So your first question is on the permutation, which was there in the last week syllabus. So just go through that. That should be straightforward. Okay. So and questions 2 and 3 basically will start imbibing in you the ideas of recursion, like how recursion can, like how powerful recursion is, right? And you can represent very simplistic, very complex, uh, you know, operations uh, in a very simple in a very simple way in through recursion. Obviously, you have to be very careful because otherwise if it ends up going into infinite loop and all of that. But other than that, it's very powerful way of writing things. Okay. Uh, Fine. So how are you finding the classes though? Are the lectures accessible? When is your exam, by the way? Do you guys know when your exam is? 21st September, right? Okay. Hmm. So anyway, so the next week content is actually quite interesting. Again, very powerful way of writing and solving problems called as dynamic programming. Um, yeah, yeah, many of the things in that can be again, will be done through recursion. Some can be done through, I mean, easier to do it using iteration and so on and so forth. We'll discuss there. Uh, but yeah. And also next week we have a session on Tuesday, that same timing like today, and we also have on Wednesday. So we have an extra session to handle any doubts that we have throughout the whole course, right? So the next Tuesday we'll discuss week seven, uh, yeah, week seven quiz solutions and week eight, concepts, and next Wednesday we'll discuss any other questions that you have on the course overall. Okay. So that'll be a last session of doubt solving. Okay. Fine. So with this, let's close the session, I think. If there are no more doubts, um, we'll close the session. Okay. Okay. Thank you for joining. I'll see you on next Tuesday.